All right. Thank you, everybody, for coming back for SummerThermoDynamics here. Now, today we are going to talk about the first law, right? But before we do that, we've spent a lot of time kind of zooming in on how to fix states, right? How to find this specific internal energy. So at this point in the class, I just want to zoom out a little bit and kind of ask this question, right? Why should you care? Right? And this is a question I think that we should always be asking in the courses that we're taking. Why are we actually learning the thing that we're trying to learn here? Right? So it turns out that thermodynamics is kind of an important thing for, in everyday life, right? So if you're going to be an engineer working in something like power generation, so this is either a coal-fired or a nuclear power plant, I'm not sure. Based on the size, maybe it's coal, I'm not sure. Here you see these big stacks, right? And we'll learn that these stacks are actually condensation towers, right? So we put steam in the bottom of these, and we want that steam to turn into water so that it kind of rains back down over here. We'll learn about how these kind of power plants work, how coal-fired power plants work, how nuclear power plants work. We'll look at natural gas power plants, right? So if you read about how the United States is reducing its greenhouse gas emissions, this is mostly because of a shift from coal-based power plants to natural gas power plants. Now, like with every other decision, what we learn as engineers is that there's always trade-offs, right? So we reduce greenhouse gas emissions by moving to natural gas. But we have to deal with the problem of how we get natural gas out of the ground. So you've probably, or at least potentially, have heard about debates about things like fracking. That's a little bit beyond the scope of the class. But we will learn about how natural gas power plants work. And then we find out that natural gas power plants work almost the same way that airplanes work. So we'll learn about these turbojet engines in airplanes. We'll learn about auto and diesel cycles, so basically how the engine in automobiles work, right? And all of these things have something in common, these three things, right? Whether it's a nuclear power plant, right, or a coal-fired power plant, or a natural gas power plant, or an airplane engine, or an automobile engine, what they're all doing, right, is they're burning something, right, or generating heat in some way, and we're trying to turn that heat energy into mechanical energy. Right, often in the form of some shaft that's going to be spinning, right? Whether that shaft is then a drive shaft that's making pistons go up and down, right? Or maybe that shaft is turning a compressor inside a jet engine, right? Or in a natural or in a coal-fired power plant, that shaft is then hooked up to something like an electric generator so that we can put power out onto the grid. All of these machines are doing the same thing that steam locomotive was doing. It's generating heat so that we can turn that into mechanical energy. We'll also talk a little bit about sort of doing that process backwards, right? So we'll talk about things like air conditioners and refrigerators, which are also super important for kind of everyday life, at least refrigerators, right? You can get by without an air conditioner, even though even in places that get cold like Rochester, that can be difficult in the summertime. You certainly don't need an air conditioner. But it's interesting, right? Because there we sort of turn thermodynamics on its head, where usually we're trying to put heat in to get mechanical work. What your air conditioner or your refrigerator does, the reason you have to plug it into the wall is that it's taking electrical energy, turning that into mechanical work in a compressor somewhere in the system, and that's making it not so that you can force heat to go in the wrong direction, because heat always travels from high temperatures to low temperatures. But what a refrigerator or what an air conditioner does is it's a device that splits itself kind of into two, where there's a cold side that's colder than the cold place you're trying to keep cold, right? And then there's a hot side where you're rejecting heat to the ambient, right? If you ever stick your hand behind your refrigerator at home, right, then it'll be hot back there. Or if you have something like a window air conditioner, right, and you can get to the other side of that air conditioner, you can feel that the air that is blowing outside is hot, while the air that is blowing inside is cold, right? So we'll learn about how all of these things work, right? So it's not just going to be about linear interpolation and finding numbers on tables, right? I get that that can be tedious and maybe a little bit boring, but it's important to remember that that's a means to an end, right? We're trying to learn, we're filling up our toolkit so that we can start to look at processes like this, right? So the way that I'm going to try to teach you how to do this, right, is a very systematic approach. It's sort of a very engineering level approach, right? So let's say we take even the most complicated nuclear power plant, right? It's going to be a series of individual components, right? And each one of these components may be a pump, a boiler, that's where we boil water, a turbine, that's kind of like a windmill, right? It's got fan blades in it, and fluid is moving over those fan blades to turn a shaft. And then a condenser, which maybe not surprisingly condenses liquid, right? Takes steam and turns it back into liquid by removing heat, right? So what we're going to learn about is that each one of these processes is like a Lego brick, right? And what you get to do as a designer, right, as an engineer, is you get to put these Lego bricks, which are each doing a particular process, a thermodynamic process, you get to put them together in different ways, right? So maybe if you're working on a power plant, you're interested in how do I increase the power that I generate faster than I increase the amount of heat that I have to put in, right? So my efficiency is getting better, right? Or maybe you just want to keep the same amount of power with less input heat, right? So that's, again, more efficiency. So eventually, we're going to learn how to do these Lego blocks, right? That's the process, right? We're sort of doing that with the first law now, although these are open systems and we're talking about closed systems, right? So each one of these Lego blocks is like a thermodynamic process. Eventually, we're going to put them together to do cool stuff, like make refrigerators or air conditioners, right? But for right now, we're just trying to learn how to do a single process. And what we've been doing over the last couple classes is less about even the whole process and more about, like, how do I understand what's going on at each little pip, right? How do I understand how much internal energy is locked up in that mass at a given time, right? And in order to do that, we need to know what's the fluid, right? And if that fluid is water, then I need to know what's the phase of that fluid, right? And eventually we'll start to talk about, I think reasonably soon, we'll start to talk about ideal gases in there too, because unless you've got a really funky automobile, there's no steam running around inside the engine in your car, right? So we need to know how to deal with things like air as well, right? So part of this we were talking about last class, right? We got to this point, and I know we went through it reasonably quickly at the end, where we were dealing with compressed liquids, right? So liquid water, right? And it was at 80 bar, and we had some enthalpy, right? But the problem was we didn't have a table for 80 bar. We had this table for 75 bar and this table for 100 bar. So we kind of had to make our own table at 80 bar, right? So we could see that 80 bar is 20% of the way between 75 bar and 100 bar, right? So we could use this kind of interpolation equation, right, after finding our interpolation factor, and we could make a table for 80 bar. So I could say, oh, if this liquid was at 80 bar, then I would know its specific volume, its specific internal energy, and its specific enthalpy. But that didn't help us yet, because we actually wanted to know what was going on with that fluid if its enthalpy was 181.95. Right? So what we wanted to know inside of our table, we know that we're somewhere in between 40 degrees and 80 degrees, but we don't know the temperature yet. Right? And, you know, I guess more importantly for the second law, or for the first law, we don't know what the specific internal energy is yet. So I couldn't put that into my equation. Now here, we could define another interpolation factor, looking at this 181, how far between the range of 175 and 341 is this number, right? We can do the math, and we see that it's, 4.5%, right? So it should be closer to 40 degrees than 80 degrees, and if we went through our table, we'd see that that's true, right? So we could find now a specific internal energy, and we could put that specific internal energy into our table, right? It's a lot of effort to get one number in our equation, right? So, but we could do it, right? We have the skills now to do that, right? Or maybe we're just learning how to use skills that we already had, right? So some sort of reasonably basic arithmetic, and putting it together to find something like specific internal energy, right? So we fixed all the states, right? That was last class's example. And it's a lot of work if we have to do this double interpolation, right? So maybe what the engineer says is, you know, when they have these double interpolations, is there some way that I can avoid doing that? Not because it's hard, right? Although it is hard. It's kind of, maybe hard's not the right word. It's not complicated, right? But just because something's not complicated doesn't mean it's easy, right? So if you're like me, particularly on exams, when you're trying to go reasonably fast, all that algebra is really easy to make like a clerical mistake because you sort of have all these different steps, right? You just have to make one mistake and then the whole thing goes down, right? So today we're going to talk about specific, you know, again, what's inside of our system if we have an incompressible substance. Then we'll find that we have another trick that we can do, right? So the math is kind of tedious, so we're going to try to avoid it if we can. So what we know so far is that we're trying to look at the universe, right? Maybe not the whole universe, just part of the universe, right? That's our system, right? Our system communicates with the surroundings. It can transfer energy to the rest of the universe, and sometimes it can transfer mass, right? So we have to answer these three different questions. The first is what's in the system. That's going to be important for our delta E side of the equation, particularly as we start to talk about internal energy. Is the system open or closed? So can mass come in or out, right? Up until we get to the first exam, the answer is going to be closed. Now, because the answer is closed, then we can use this version of the first law to figure out what happens to the system. So we know that over time, the energy stored in the system will change. Now, does that change in energy come because of heat transfer or because of work or maybe because of both, right? So what are our steps? The first thing that we'll do, I always want you to write down the base level of the equation because I want you to get into the habit of writing down your assumptions, right? That's really important. So we'll write down delta E is equal to Q minus W. Then we'll write down the assumptions that, well, maybe potential and kinetic energy are not important. These are assumptions we'll often make, which is different than assumptions that we always make, right? But often we will say that potential and kinetic energy are not important. And then delta E will become change in internal energy, right? We know now how to find the work. It's the integral of P dV. And we know that delta big U, or the change in internal energy, is equal to the mass in the system, which we know is constant, in this case, times the change in specific internal energy, right? And if we can find the specific internal energy, if we know what's in the system, so is it water, is it a liquid, is it a vapor, or is it some combination, right? What's its temperature and pressure or quality, right? Then maybe we can find the heat transfer, right? We've talked about how to find delta U, or this change in internal energy, and it involves looking at these TV and PV diagrams and figuring out what's in the system, right? If it's under the vapor dome, then you want to use your quality equation, right? So here, no matter what property you're talking about, unless it's temperature or pressure, which are dependent, you'll use an equation that looks like this. U is a function of quality, and we take UF plus quality times UG minus UF, right? And we showed how this is just a linear combination, some percentage of vapor and some percentage of liquid, right? But they're both at that saturation point. Now, if you're not under the vapor dome, if you're either liquid water, right, or this compressed liquid, or you're superheated vapor or steam that's past that saturation point, then we can find an interpolation factor, right? So we can find this A, right? So let's say I know the pressure and temperature of a given steam, right? Then I can define this interpolation factor by the temperature on my table, right? And I can find what percentage of the range of temperatures did I go. And because we're going to assume that properties like specific internal energy are going to be linear between the points that we have on the table, we can say, oh, if I went 20% of the range in the temperature it also means that I had to have gone 20% of the range in the specific internal energy. So I can use this equation, which actually looks a lot like that quality equation. Right? Now, sometimes when we're in the tables, we get these subcooled liquid problems, like we did last. Right? And you'll see that there is way more information on the tables for steam, superheated vapor, than there is for this compressed liquid, right? Or subcooled liquid, right? So here, we'll often have to do double interpolation because we won't have the right table and the temperature we're looking for won't be a row on the table. So we'll probably have to interpolate with temperature and pressure. Although last class we saw what we interpolated with pressure and specific enthalpy, right? So we know that this is kind of a tedious process. So if you're like me, right, as an engineer, it's not that we're lazy, but we want to be efficient, right? So we might ask the question, do I really have to do this, right? Is there some way where I can get an answer that's good enough for whatever my application is, right, that doesn't involve such a tedious process, right? And the answer is, well, sometimes. Sometimes we can avoid doing this double interpolation. Particularly, it depends on what your application is, right? So if what you're trying to do is heat up some water that goes into a hot tub, right, then your accuracy, if you're off by a degree or two, it's probably not a terrible thing, right? But if you're trying to, I can't remember, was it Blue Origin? Somebody landed a satellite on a passing asteroid, right, a couple years ago. That's a pretty big deal. I'm guessing that's not a simple problem, and you probably want to be pretty precise in that particular application, right? So if that's your application, then you might want to go to the double interpolation because that's probably a more accurate representation of what's going on. So part of our job as an engineer, right, part of the reason that people are going to people are going to hire you not because you can do problems in the back of a textbook, although that's important, right? The reason that that engineers have a value when you graduate, right, and for the rest of your career, is because we're going to try to teach you how you can take a normal everyday thing and make it look like a problem in a textbook, right? And then, once you're the senior engineer, then you can give that problem to the co-op that you just hired, right? And they can pound through and do the data. Or maybe, I don't know if any of you have the Wolfram Alpha app, right? It's pretty useful. And I think there's even a free version of it. It'll do a lot of the homework problems that you'll have in engineering, right? And it's funny when I tell people that, there's sort of two camps, right? Some people are like, awesome, that means it's going to do my homework for me, right? And the other camp is like, well, why is anybody going to hire me if they can get a free app that's going to do all these problems for them, right? And the reason is, the value that you're going to bring to your employer will be the ability to take, you go talk to an operator on the line and they describe a process to you, and then you go back and you turn it into something that looks like the homework problem that Wolfram Alpha problem can solve. Right? So that's what we're trying to do, right? And that's why we hammer so much this this kind of homework process, because what it's really doing is teaching you how to systematically break problems down into manageable pieces, right? So do we have to do this double interpolation? Not always, right? So if we have an incompressible liquid or a solid, so what does this mean, right? So a solid, if I have a block of wood, let's say, right, and I push really hard on it, right, from both sides, its shape doesn't change very much, right? Its density doesn't change very much, right? And if that's true, then it's also true that its physical properties don't change very much. Now, if I fill my bathtub up with water and I do the same thing, and maybe I put like some kind of, I don't know, maybe I wouldn't use plywood because it's kind of expensive now, right? But if I could, put some kind of covering on it and uniformly add pressure onto the water in that bathtub, the water is not going to compress very much. It's not going to change shape. Its properties like density are not going to change very much. That's a lot different than if I have a piston that's full of, say, air, right? And I close that piston up, and I push on that in that piston. If I close the valves up in the piston cylinder assembly and I push the piston in, it's going to compress, right? Or you can think about it, if I have air inside of a balloon, right? I can push that air together, right? And as I push that air together, its density does change, right? Its volume does change. Its properties will change. So gases are typically compressible, but liquids are typically, we can think of them as being incompressible, and solids are also generally incompressible. So for these incompressible materials, things like liquids and solids, then I can use these definitions for specific heat, right? So CV, this is specific heat at constant volume. And that's going to be equal to the partial derivative of the specific internal energy over the partial derivative of the temperature, right? CP is kind of the same thing, but with pressure held constant, right? Now this is the partial of H, partial T. And then we have this specific heat ratio, which we call K, which is CP divided by CV. Now you'll find these properties, maybe, I think it's maybe table A1 in your textbook, but there's some textbook table that will give you properties, specific heats. Right, so what does this mean? So let's look at CV, right? Because we're interested in the closed version of the first law, where we're trying to find specific internal energy, right? So I could write CV equals this equation, right? But then from separation of variables, I can make CV dt is equal to du, right? Now, if I assume that the specific heat is constant, right, then I can integrate both sides. Well, integrate both sides, assume that specific heat is constant, move it out, and then I get the specific heat times the change in temperature is approximately equal to the change in the specific internal energy. So this works provided that the fluid I'm talking about, or the thing that I'm talking about, is incompressible, and provided that the specific heat is constant. So this is the kind of thing that you need to understand in this class, right? You've got all of these equations. These equations, they're like behind locked doors, right? And in order to open the door and get the equation, you need to write down the assumptions, right? So the assumptions for using this equation are that the fluid is incompressible and the specific heat is constant. So if I write those things down, then I can say, oh, remember, every time I write down an assumption, I'm taking one step further away from reality and one step towards whatever cartoon of reality I'm trying to make, right? So now I have CV times delta T is equal to this change in specific internal energy, or approximately equal, right? I could do the same thing if I was trying to find specific heat, or if I was trying to find the change in specific enthalpy. Then I would take CP times delta T. So this is important, which one goes with which. You could derive this if you wanted to. But I think you can see on the equation sheet, these equations are probably there, right? So here, what I remember is that CV goes with delta U, because the V looks a little bit like a U, right? Maybe I'm stretching it a little bit there, right? And that delta H, I had a student, she told me once, oh, I remember that delta H goes with CP, because H is enthalpy, right? And this is CP, so CP goes with enthalpy, right? So you can only use these equations if it's an incompressible substance, right? Or specific heat is constant. But the nice thing about incompressible substances, right, so solids and liquids, is that CP and CV are basically the same number, right? So actually, we'll get to a point where we can sometimes use these for gases too, but for gases it really matters which specific heat I use, right? But in this case, for liquids and solids, CV and CP are about the same. So let's go back to this last problem that we did, right? So we did this double interpolation to find this sixth state last time, right? So we knew the temperature was something and that the specific internal energy was something, right? So this is the more exact solution, this U6. We found this by double interpolation, right? But we also knew that the pressure was 80 bar. So here's one way that we could try to find the specific internal energy in this case. So if the pressure here is 80 bar, I can go to my two-phase tables and I can find UF at 80 bar, right? So at 80 bar, this is going to cut across the vapor dome at some point, and I can find the specific internal energy right here on that saturated liquid line. Right? So in this case, that temperature is 294 degrees Celsius, and I know UF. Now, because now in this case, I could make up a process where I'm going from this only liquid state, so it's compressible, or incompressible, sorry, only liquid state, all the way down to here, which is another only liquid state, right? So it's compressible or incompressible on both sides, right? I couldn't do this across the vapor dome because once I start to go across the vapor dome, I start to get vapor in there, and that vapor is compressible. So I can't use CV delta T across the vapor dome if I have any kind of vapor inside my system. But here I'm going just from one liquid state to another liquid state. Right? So here I can approximate this U value because I know this U value here and I know delta T if I can look up CV. Right? So I look up CV in the textbook. CV for a temperature that's the average temperature here that we're looking at, right? I just have to pick a temperature. Sometimes I don't know what that other temperature is, right? So I just have to kind of guess, right? And if I wanted to, I could iterate back through and see if my first guess is any good, right? But these things, they tend not to change very much. We say that the specific heat is often a weak function of temperature. That's engineering code words for the temperature doesn't change, or the specific heat doesn't change very much with temperature. It's a weak function, so it doesn't change very much. Then I could approximate this specific internal energy down here as UF, this F, minus CV times the change in temperature between this point, which I know, in this point. Right? So here, let's say that I knew this temperature, right? Because I only found that out after I did the interpolation. But if I did know the temperature, then I could put that in and figure out an approximation. Now, here, I can see that I'm in the ballpark, right? So 200.5 kilojoules per kilogram, but the kind of quote-unquote real answer is 174.7 kilojoules per kilogram. But even that's not exactly the real answer, because in order to get this answer, which I think is more accurate, because I got it just from the tables, right? I'm still assuming that the function for specific internal energy is linear between those two temperatures, right? So there's some error associated with this, right? But I made some more assumptions, so there's even more error associated with this number, right? So here we can see from this approximation, this was much faster to do, but you know, because we took these extra steps, we added these extra assumptions, we added another 15% in this case of error to our answer. Now, depending on what your application is, maybe that 15% is a deal breaker. Maybe you can't accept that, right? But if it's kind of a low risk situation, right, or you're adding some other factor of safety on top of whatever your final answer is, maybe you look at that and say, 15%, that'll be acceptable for my application, right? That's another reason why they pay engineers money when you graduate, is because you'll have to make judgment calls like that for whatever application you're working on, right? So, you know, you'll be a decision maker as an engineer, right? So you'll have to decide if adding that kind of uncertainty is acceptable to you, right? Now, is there another way that we can avoid using double interpolation and still get a pretty good answer, right? And maybe I wouldn't ask the question if we didn't have another answer, right? But for a given pressure, we will assume that the specific internal energy at a temperature, or at a temperature and pressure, we'll say that the pressure doesn't really matter very much. We'll approximate for a subcooled liquid that the specific internal energy at that temperature is approximately equal to the saturated liquid specific internal energy at that same temperature. So here what we're saying is that specific internal energy is a strong function of temperature, that it changes a lot with temperature, or appreciably with temperature, but it's a weak function of pressure. So that if it's a subcooled liquid, I don't much care what the pressure is because it's incompressible, right? That the properties don't change very much in the bathtub, no matter how much I'm pushing on top of that interface, right, between the liquid and the air. That it's really only the temperature that I care about. And that I can say, if that's true, then, you know, if I don't care about the temperature, it's easy to find the saturated liquid value of the specific internal energy, because I can just look on table A2, right? So let's check this out, right? So here, I'm just going to say a temperature of 100 degrees, right? This is a temperature we know and love, because that's where water boils at, right? So if I actually have saturated liquid at 100 degrees, right, then its pressure is 1 atmosphere, right? So there's no error here. It's correct because I looked that up on the table, right? But now what if I increase the pressure to 25 bar? So now the water's not boiling anymore, but it's still at 100 degrees, right? But I'm pushing it in, so it's harder for those water molecules to separate into vapor, right? I've increased the pressure by a factor of 25, right? So this is the same as if you were, right? If you're scuba diving, I don't know if anybody's a scuba diver. I'm not, but I do know that every about 10 meters that you swim down in water, you you add 1 atmosphere of pressure, right? So we're getting up to like 25 atmospheres. So that means that you're down like what, 250 meters or something, if I'm doing the math right? Right. So this is a pretty dramatic pressure increase, right? You certainly feel it in your ears, even if you're down like 5 meters, you feel it in your ears, right? Right. So here, right, this is like more than 2.5 football fields down in the water. You still basically have the same specific internal energy, right? Your 0.2% error here, right? You double that again, you go 500 meters down, right? Now you're 0.3% error, right? We go up to 75 bar, still not even a percentage of error, right? 100 bar, right? These are huge pressures now, right? They're very big pressures, right? Even if we get up to 300 bar, we're only adding 2% error to this value, right? So this is my way of trying to convince you that this assumption is a pretty good assumption for liquids, only for liquids, right? If you have a liquid and you know the temperature, it doesn't matter what the pressure is too much. It does matter. You can see these numbers are changing, but it doesn't matter too much. You can approximate that specific internal energy as if it were a subcooled liquid at the same temperature. Right? So now we have 2 different strategies for liquids, right? One is if we know the temperature difference, we can pretty quickly say CV times delta T is approximately equal to the change in specific internal energy. But if we want a more accurate answer, and we know both the temperatures from the liquid to the liquid, right? Or if we're going, say, from a liquid to a vapor, then we have to not look at delta U, we just look at U for the liquid, right? We can approximate that as UF at whatever temperature we're at, right? So this is a pretty good method, a method that we'll use pretty consistently, right? It works very, very well for specific internal energies, right? As we can see here, but it still works pretty good for enthalpies too, right? If I was drawing this out, what I'm saying is on this TV diagram, even though the point that I'm actually interested in is over here, right? The pressure is higher than if it was a saturated liquid, but it might as well be this point, that U doesn't change very much as I increase my pressure on this constant temperature line. Right, so this is true for specific internal energy. It's still mostly true for other properties too. You can see here for the specific enthalpy, if we do the same thing, we actually happen to get the same number here. But while there's basically no error or very little error in the specific internal energy, the error for the specific enthalpy does come out to be around 4%, right? So this is a better approximation for specific internal energy than it is for specific enthalpy, but it's still potentially reasonable to do, right? So this is generally, at least in this course, an acceptable application or an acceptable assumption if we're talking about subcooled liquids, right? You can't do this if you're under the vapor dome, and you can't do this if you're a superheated vapor, right? So the good thing here is that when we make this assumption, either of these two assumptions, it makes our lives easier, right? Particularly if you're on an exam question, right? If you're on an exam question and you're like, oh, I got to do this double interpolation, right? That's going to take me a long time, and I only got about half an hour to do this problem, right? But it's much faster to just look up UF at whatever temperature you're at, right? So it takes a lot less time, right? So that's good if you're in this time pressure situation of something like an exam. But it also means that there's less chance that you make an arithmetic mistake, right? The other good news here is that it is a reasonable assumption, right? Like, we wouldn't really say that you should do this if we didn't think it was a reasonable assumption to at least consider, right? The bad part is, like all assumptions, every time we make an assumption, we walk further away from the truth, right? Whatever the ground truth is, we turn that, that actual car engine to like the Lego model of that car engine, right? It's not real anymore. But that's not really our job necessarily as engineers, right? I think really what we try to do as engineers is we try to either design or improve particular processes with the burden of having incomplete information, right? So that's kind of what we're trying to do in this class, is try to develop some engineering intuition where we can see, what kind of assumptions are reasonable to do so that we can take this problem that's actually probably we can't solve because we don't have enough information. How do we make it so that we can get a reasonable answer to that problem, right? Something that we can practically use to do something like improve the efficiency of an internal combustion engine, right? So that's the kind of problem that we're looking for. We're not looking for purity here. We're not looking for the perfect answer. As engineers, we're looking for reasonable answers that are good enough to have some kind of practical advantage, right? So like I said, the other good part here is that this is a reasonable assumption, right? I wouldn't be teaching you this thing if it wasn't a useful thing to do sometimes. But keep in mind, every time you make an assumption, you're sacrificing some accuracy. So depending on what your application is, you may want to go back and look at the assumptions that you made. This is actually a pretty common thing. If you're designing something, you write down all the assumptions that you make a prototype, and your prototype didn't act the way that you thought it was going to act. So what you do is you go back and look at your assumptions, because what that means, right, is that this model that you built of the world, right, your kind of Lego model, didn't do what you thought it was going to do, right? Your understanding of the universe was somehow lacking, right? So then you look at your assumptions and you kind of look at the ones first that you think, well, that one was a bit of a stretch, right? What if I relax that assumption and I make the problem a little more complicated? Do I then capture some of the physics that maybe I was ignoring before, right? So that's kind of what we're doing. We're building these mathematical or physical models of the world, which aren't exactly what happens in the world, because the world is generally too complicated. So we're going to do an example with our last 10 minutes or so here, right? And it's this example here. This is an isolated system, right? Or at least mostly isolated system. It's at least insulated so that there's no heat transfer between our system and the surroundings. We're told that we have this resistor, which is connected to this copper mass, right? This is our heater. And then inside we have some water, right? So the copper is initially at 20 degrees, and we have 13 kilograms of copper. The water is initially at 50 degrees, and we have 4 kilograms of water. And we add some kind of energy through the resistor, right? So there's current going in here, so we're adding some kind of energy into the system at 100 kilojoules. And what we're asked, eventually this comes to equilibrium, right? I don't know if we've used this word yet in the class. Maybe it was in the original lectures. But what equilibrium means is that, or steady state sometimes, means that things are not changing with temperature. So at equilibrium, right, or at steady state, this copper temperature will essentially be the same temperature as this liquid, as the liquid in the reservoir, right? So we're going to try to find this final equilibrium temperature. So at what point, when we add this energy in and the energy's had a chance to kind of, find its own equilibrium, what's going to be the final temperature of the water? So I'm going to move from this PowerPoint into the Word document here. So what do we do here, right? So the first thing, if you don't know what's going on, right, in a particular problem, the first thing I would suggest you do is, you draw a schematic, right? So our schematic looks like this, right? So what's going to happen here over time? And we don't really have to worry about what the trace of these look like, but over time, we expect, right, we're going to add energy, so this copper temperature is going to increase over time, right, and eventually flatten out. And the water temperature, let's say it maybe would decrease over time and come to some constant temperature. This is definitely what would happen if we weren't adding energy to the system, right? Let's say you had, instead of an ice cube, let's say you had water, right? But the water was hot because it had been left out on the deck or something, right? So it's, I don't know, maybe 20 degrees Celsius or something. But you have this frozen cube that's maybe -4 degrees of stainless steel that was in your refrigerator, and you put it into the water. What's eventually going to happen over time is that frozen cube and the liquid water will come to the same temperature. They'll eventually get to some kind of equilibrium, right? As opposed to an ice cube would just melt. So I didn't use that as an example, right? Because there's no phase change happening in this problem. But because we're adding energy into this system, we don't know where this temperature is going to be, right? This temperature, we're pretty confident it's not going to be below this 25 degrees, but it could be in between these two values, and it could even be above 50 degrees because we're putting more energy in. If we weren't putting more energy in, I would be, we would know that the temperature would be between 50 and 27. Here it could be above 50. Right, so now we've drawn this schematic. Let's say I still don't know what to do. Because this is thermodynamics class, even if let's say it's an exam and you have no idea what to do, write down the first law. Because in this class, thermodynamics class, the odds that you will have to use the first law of thermodynamics in your answer to whatever problem that you're facing are really, really, really high, right? So our first assumption is going to be that this is a closed system. And because this is a closed system, then I can use this version of the first law, which is the only version of the first law that I know, right? So this is always a good assumption for us, particularly before the first exam, right? Now, so I know that delta E is equal to Q minus W, right? But delta E, this is the change in the energy in the system, and I have two different masses here. So I write this out as the change in energy in the copper plus the change in energy in the water, right? So now I'm going to write down some other assumptions here because I don't like this delta E term, right? So my mass is basically not moving, right? Or at least if it was, let's say it's on a truck or something, we're going to assume that it's not accelerating, that the kinetic energy is not changing. So if delta KE is equal to 0, and if delta PE is equal to 0, and if you want to put spring energy, you can put that in there too. And then my equation, my governing equation here becomes U2 minus U1 for the copper plus U2 minus U1 for the water is equal to Q minus W. Sorry, my W is kind of small there, right? But I can do a little bit better than this, right? I guess I'll keep drawing in red, right? Because I know that this is delta big U, right? So this is going to be the mass of the copper times U2 minus U1 plus the mass of the water times U2 minus U1. This is of the copper, and this is of the water, is equal to Q minus W. Now, the problem also told me that it was perfectly insulated, right? We have a special engineering decoder ring word for this, right? So you could write down insulated here, but I'm going to write down the fancy engineering word here, adiabatic. Now, my spelling is terrible, but I think I got this right here, right? So adiabatic means Q is equal to 0. There is no heat transfer between the system and the surroundings. So this is pretty good, right? So far, there's not even really all that much I know about what I'm doing, but Professor Scherzer told me if you don't know what to do, write down the first law. And then start to make some assumptions, right? These ones, at least before the first exam, you're probably going to make these most of the time, right? That'll let these delta E's turn into delta U's, right? And then I read the problem again. It said that it's insulated. So Q must be 0. Right? Now I got to pick, right? So now I can either, I got a choice here, right? I can either go for the work, or I can try to find delta U. I'm eventually going to have to do both of these things, right? Does anyone have a preference? Okay, let's do the work first. Work, right? Normally we'd want work is the integral of PdV, right? But this problem doesn't tell us anything about pressure volume relationships, and it's not a gas, right? It's a liquid, right? But it does tell us this, right? The electrical system, or the electrical resistor, transfers 100 kilojoules of energy into the system. Now, I might want to call that heat, or I might want to call it work. I'll show you that it doesn't really matter. But I'm going to call this the work, right? So this is energy in, right? So I think hip to win. So I'm not going to use this equation, even though I often would, right? But I won't this time. I know hip to win, work in is negative, and here we have 100 kilojoules in. So if this is work, then it's negative 100 kilojoules. And if I have my equation, right, it was delta E is equal to Q minus W. This we've changed since, right? This is delta U of the two different things. But here, if I put this in, right, then I've set this equal to 0. So if this electrical stuff, if I call this work, I'm going to get delta E is equal to negative, right, because it's minus W, negative 100 kilojoules, right, which is plus 100 kilojoules. Now, I don't know about you, but when they taught me about circuits, we talked about I squared R. We talked about that as heat loss, right? So let's say that I want to say if this electrical stuff was heat, then I would say work is equal to 0. Both of these are okay, right? Then I would say that delta E is equal to Q minus W. This would be 0. Okay, thanks, Dan. I'll post the lecture notes. Right? The work would be 0, and then heat would be 100 kilojoules, but it would be in heat in is positive, so this would still be 100 kilojoules. Right? So no matter what, no matter how we model that, it's the same thing. So now we're going to get, so now we know this side of the equation. Now we'll deal with this. For the copper, I don't have any tables for copper, right? So here I'm going to say that Cu delta T is equal to delta U for copper, right? So here I'm assuming constant specific heat. As I write down my assumptions here, number 5, Cu, or C for copper, is constant. And I'm going to do the same thing for water too, because that's going to let me set up the equation in a certain way, right? So now I'm going to come down here, and my equation is going to be the mass of copper times, this is U2 minus U1 of copper, plus the mass of water, U2 minus U1 of water, is equal to, this is just negative W, right? We know this, right? But we don't know these guys yet. But I'm going to assume incompressible and CVs are constant, right? So then what this equation is going to become is M of copper, CV of copper, T2 minus T1 of copper, plus mass of water, Cu of water, T2 minus T1 of water, is equal to the negative of the work. So now I was given the mass of the copper. I looked up, so this is tables. I feel like it's table 2 in your, or 1 or 2 in your textbook. You might have to look around for it. I'm given T1 of the water and T1 of the copper. I know the work now, and I know also, assume T2 of the copper is equal to T2 of the water. So here, you might have to do this, you might have to do some iteration to get an answer here. But as I went through this problem, right, so this is the same point, right? We cross this out. We got, when we put this in, this is a bit, there's some algebra that's going to be involved. You isolate for T2, right? And we find that T2 is 49.3 degrees Celsius, if you do the math, right? So this ends up being, from this equation, we can isolate T2, and it ends up being 49.3 degrees Celsius. But if you had a question like this on the exam, and even if you don't get to this final answer, you know, it's like the final answer is maybe worth something like 10% of your grade, right? Obviously, it'll change depending on the problem, right? But the process here, right, starting with the first law, writing down your assumptions, getting the symbolic solution, right, deciding how to fix delta U, how do you find work, the process that you do is worth something like 90% of the points that you'll get on an exam. So that's all that I have for you today. I'm happy to stick around for a bit if people have questions.
Thank you, Professor.
No problem.
Thank you, Professor. Have a good rest of your day.
You too. Bye-bye. Thanks, everyone.